Now let us understand a typical 4-transistor resistive load SRAM cell commonly used in high-density memory arrays. This specific design is efficient and compact, making it ideal for applications where memory density is critical. Let's break down how this SRAM cell functions. At the core of this design, we have a pair of cross-coupled inverters. These inverters form a stable latched circuit with two possible states, which correspond to the 0 and 1 binary states. This latch is fundamental to the SRAM cell because it's where the actual bit of data is stored. By having two stable operating points, the inverters reliably hold the data as long as there is a power supply. To perform read and write operations on this cell, we use two NMOS pass transistors. These transistors act as access points and are controlled by the row select signal and read signal RS. When RS is activated, it allows data to be read from or written into the cell by connecting it to the bit lines. Speaking of bit lines, this cell uses a dual bit line arrangement, meaning it has two bit lines rather than one. This complementary structure significantly enhances the reliability of the SRAM cell during data transfers. By providing both the true and complement bit lines, we can improve signal stability, which is essential in high-density memory applications. Let me now explain the operation of a 4-transistor resistive load SRAM cell by walking through how data is stored, read, and written in this structure. Let's go through the process step by step. Idle state when RS is equal to 0. When the word line, labeled RS, is not selected, its voltage is at logic 0. In this state, the pass transistors M3 and M4 are turned off. With M3 and M4 inactive, the two cross-coupled inverters in the latched circuit hold their last stable operating point, preserving the stored data bit without any changes. At this point, if none of the word lines in the SRAM array are active, the large column capacitance on bit lines C and C bar are charged by the pull-up transistors MP1 and MP2. This precharge prepares the bit lines for any future read or write operation by setting them to a known voltage level. 2. Activating the memory cell with RS is equal to 1. When we select this specific memory cell, we do so by raising the RS line voltage to logic 1. This enables the pass transistors M3 and M4, connecting the cell's internal nodes to the columns, bit lines, and allowing data access. Once the cell is active, we can perform 4 basic operations: write 1, read 1, write 0, and read 0. 3. Write 1 operation. In a write 1 operation, the bit line C bar is forced to logic low by the data write circuitry. This causes the driver transistor M1 to turn off, allowing the internal node connected to V1 to attain a high voltage level, while the other node, V2, is pulled low. This configuration stores a logic 1 in the cell. 4. Read 1 operation. During a read 1 operation, bitline C retains its pre-charged high level while bitline C bar is pulled down by transistors M2 and M4. The data read circuitry detects the small voltage difference between VC and VC bar, where VC is higher than VC bar. This difference is amplified by the sense amplifiers, producing a logic 1 as the data output. 5. Write 0 operation. To write a data to 0, the bitline C is set to logic low, turning off transistor M2. This allows the internal node connected to V2 to reach a high voltage level, while V1 goes low, effectively storing a logic 0 in the cell. 6. Read 0 operation. In a read 0 operation, bitline C bar remains at its precharge level, while bitline C is pulled down by transistors M1 and M3. This creates a voltage difference between VC and VC bar, where VC bar is higher than VC. The sense amplifier detects and amplifies this difference, resulting in a logic 0 output. CMOS SRAM cells are a major improvement over traditional resistive load NMOS cells. By using cross-coupled CMOS inverters, we significantly reduce the standby power consumption. In this case, power is primarily limited to the small leakage currents from CMOS inverters, which are much lower than those in resistive load cells. Let's look at the advantages CMOS brings to SRAM. A. Power efficiency. CMOS-based SRAM only draws current during switching, which makes it a low-power choice for high-density memory arrays. B. High noise immunity. The larger noise margins in CMOS improve overall data stability, making it more resistant to disturbances. C. Low voltage operation. These cells can operate at lower supply voltages, which is a benefit when compared to resistive load SRAM cells. However, there are a few challenges. To accommodate the PMOS transistors, the cell area tends to be larger, as it requires an N-well and polysilicon contacts. Additionally, CMOS process complexity and potential for latch-up issues can complicate design. That said, recent technological advances have addressed some of these challenges. With multilayer polysilicon and metal processes, the cell area has reduced significantly, making CMOS-based SRAM more feasible even for high-density arrays. In terms of structure, CMOS-based SRAM cells use PMOS pull-up transistors on the bit lines, which enable the column voltages to reach the full VDD level, allowing for stronger signal levels. Finally, for further power savings, a periodic precharge signal can activate the pull-up transistors, recharging the column capacitance and ensuring stable, efficient operation. Cell design strategy dictates the width-to-length ratio, i.e. the WL ratios of transistors in a typical CMOS-based SRAM cell. First, we need to understand the two basic requirements that are essential for the operation of the SRAM cell. 1. Data read operation. It is critical that reading the data does not destroy the information stored in the SRAM cell. We must ensure the integrity of the data during this process. 2. Data write operation. The cell must allow for the modification of stored information when writing new data. Let's focus on the data read operation, assuming that a logic 0 is currently stored in the cell. At the beginning of the read operation, the voltage levels within the cell are set as follows. We have V1 at 0 volts and V2 at VDD, indicating that the internal node voltage for V1 is low while V2 is high. Let us see the state of the transistors during this operation. The transistors M2 and M5 are turned off, which means they do not conduct. Meanwhile, transistors M1 and M6 are operating in linear mode, allowing for controlled conduction. As we begin the data read process, the access transistors M3 and M4 are then activated. These transistors connect the internal nodes to the bit lines, facilitating the read operation. It's crucial that all these considerations regarding transistor states and voltage levels are properly managed to ensure the correct functionality of the SRAM cell during read operations while safeguarding the stored data. This outlines the operation of the SRAM cell during the read phase, focusing on the critical behavior of the transistors involved. When the row selection circuitry turns on the access transistors, M3 and M4, the expected behavior of the column voltages begins to unfold. In column C bar, we observe that there is no significant change in voltage since M4 does not conduct any current. Conversely, in column C, where M3 and M1 are activated, we see that a non-zero current begins to flow, causing a slight drop in the voltage level. It's important to note that the column capacitance, CC, is typically very large. Because of this, the voltage decrease during the read phase is limited to only a few hundred millivolts. This small change is crucial for the data read circuitry, which is responsible for detecting this minor voltage drop and amplifying it to represent a stored 0. As M1 and M3 gradually discharge the column capacitance, we observe that the node voltage V1 begins to rise from its initial state of 0 volts. However, if the width to length, WL, ratio of M3 is significantly larger than that of M1, there is a risk that V1 could exceed the threshold voltage of M2. If this occurs, M2 could unintentionally switch on, altering the stored state, which we want to avoid. Therefore, a key design consideration for the read operation is to ensure that V1 remains below the threshold voltage of M2. This is vital to keep M2 turned off during the read phase. Finally, we can assume that once the access transistors are engaged, the column voltage Vc will remain approximately equal to VDD. In this scenario, M3 operates in saturation while M1 functions in the linear region, which maintains the stability of the SRAM cell during read operations. We have discussed the implications of aspect ratios in the SRAM read operation, particularly focusing on transistors M2 and M3. We begin by acknowledging that the upper limit of the aspect ratio discussed earlier is actually more conservative than initially thought. This is because part of the drain current from M3 is utilized to charge the parasitic node capacitance at node. This detail is crucial because it implies that the actual behavior of M2 may be influenced more than anticipated by the conditions present during the read operation. In terms of functionality, we need to ensure that transistor M2 remains in cutoff during the read 0 operation. This will only occur if the specified conditions regarding the aspect ratios are satisfied, ensuring that M2 does not inadvertently conduct when it should be off. Additionally, it's important to highlight that a symmetrical condition also governs the aspect ratios of both M2 and M4. This symmetry is vital for maintaining balance within the circuit, ensuring that both transistors operate optimally under the defined conditions. Now, we focus on the write 0 operation within the SRAM cell. To start, let's establish the initial state having a logic 1 stored at node 1. Our goal in this operation is to change this stored value to 0. The first critical step is to reduce the voltage at node 1, denoted as V1 below the threshold voltage of transistor M2. This threshold is represented as VT2. When V1 drops below VT2, transistor M2 will turn off, effectively isolating node 1 from influencing the rest of the circuit. As V1 decreases, we observe that the voltage at node 2, which we call V2, starts to rise. This rising action occurs because, with M2 turned off, there's no longer a path to hold V1 up, allowing V2 to increase. An important moment occurs when V1 reaches the threshold voltage of the NMOS transistor, noted as VTN. At this point, M3 transitions into the linear region, meaning it can begin conducting a controlled amount of current. Simultaneously, M5 enters saturation, which indicates that it is fully on and effectively enabling the desired write operation. During the write 0 operation, transistor M2 will enter cutoff mode if condition as in EQ P is met. This ensures that transistor M1 is subsequently turned on, allowing the stored information to be changed. Additionally, a symmetrical condition also governs the aspect ratios of transistors M6 and M4. The 6T SRAM cell is essential for fast, reliable data storage due to its stable design and low power requirements. Today, we covered how the 6-transistor configuration enables efficient read and write operations, ensuring data integrity without refresh cycles, a distinct advantage over other memory types. We looked at each transistor's role in stabilizing stored data, as well as conditions needed to maintain reliable read-write performance. This design is foundational for applications like CPU caches, where speed and stability are crucial. Thank you for being part of this session. I hope this fundamental exposure provided a clear understanding of SRAM's significance in modern memory technology.